guys that keep up on drugs. And we got another
Okay, so good morning, everyone.
Good morning.
So today we're gonna continue this example quickly. Okay, we don't have much left in this example. Okay, we're almost done. I'm sure you know how to continue, but just to make sure you know how to solve this problem right to the end. So in example 8.3, we solved the same example. Okay. But we didn't make use of the load cases for the life load. So the shear force diagram that we got is this blue one, okay? This is what we got. Now, applying the life load so that we maximize the shear force at different points, or actually to maximize the shear force at the midpoint, this is what we get, the red curve, okay? The shear here is not maximum. The maximum was 108. This is just 50.4. But now the shear is right in the middle. It's the maximum value that you can get just by applying the life load on that half, okay? So it's 16.8 right in the middle. To maximize the shear force at different points, you would put the load at, apply the life load on different lengths, okay? So actually what you get, okay, by applying the life load on different lengths, okay? So for example, let's say you have another load case, okay? Let's say a load case where you apply the life load here. When you apply the life load here, that will maximize the shear at that point. And you will get, like, for example, this value, okay? So the envelope of all those cases is this green line, okay? Connecting the maximum value of the shear at the support here, which is 100.8, and the maximum shear right in the middle is 16.8. Connecting this will give you the envelope for the maximum values of shear at different points between point A and point C. Okay? So now, this is the envelope. So now, this is the center line of the beam. The shear here is 100.8 K, and the shear here is 16.8 K, and right in between, okay, that's the envelope. So this is A to C, this is 7 feet, which is 84 inches. I cannot call this the shear force diagram. This is not the shear force diagram. This is the envelope of the maximum shear force. Okay? So this includes many shear force diagrams, just the maximum for each case. Okay? This is what you would use to design the beam here. Okay? So if you have this envelope of the maximum shear force diagram, how would you design this? We're just going to follow the same steps as we did in the previous example. So how much was phi VC? This is from the previous example. It's not going to change. Phi VC is 32.18 pounds. Okay? So phi VC divided by 2 is 16.09 K. As you see here, the minimum value for the shear is 16.8, which is larger than phi VC divided by 2. That means that you have to provide stirrups, okay, everywhere in the beam. This is larger than the 16.8 K at the midpoint. What does this mean? It means that stirrups
16.09 or 16.9?
16.09.
Less than 16.09 is less than 16.
Yes, yes. So again, stirrups should be provided everywhere. Okay? You cannot stop the stirrups. Okay, in the previous problem, when we didn't include the effect of the, the live load location, we actually realized that the shear right in the middle of the beam was 0, so you could stop the stirrups at some point, right? When the shear force becomes less than 16.09, you can stop your stirrups. While here, no, you cannot stop your stirrups, okay? Based on that, load case for the live load cases for the live load. So now, I'm going to divide this into, again, we're going to do the same. We're going to divide this into 3 spaces, okay, 3 places here. Somewhere here where you need the maximum stirrups or the minimum spacing, and then just somewhere in the middle here, and then a third spacing, okay? 3 different spacing. I'm going to use 3 different spacings here, okay? So the first here, the spacing in the first region should be designed on the maximum shear here. How much is the maximum shear you would consider for design?
100.8.
No.
Oh, it's
You have to move by distance d from the support. So that's what we should do now. Move at a distance d. How much was d? 22.5 inches? 22.5 inches. So at that point, how much is the shear? So to find the shear here, what's the equation of that line? What's the equation for that green line here?
So 100.8 minus 100.8 minus 16.8 divided by 84 with 12 x.
Exactly, okay? But I'll, instead of dividing by 84, that's in inches, I'll just divide by 7 in feet, okay?
84 divided by 12, yeah.
Okay? So the equation here, you start by 108 and then you go down, right? So this equation, the equation of this line, let's see how we got this, okay? The equation here for this line, it's 100.8K, okay? And then minus, okay, some value. The value that you're subtracting increases at this distance increase, right? So it's minus something multiplied by x. It's linear relationship. How much is the number over here? It's the slope of that line, right? How much is the slope of that line? It's the difference in y multiplied by the difference in x. The difference in y, the difference in x is x.
No, you said difference in y multiplied by x.
No, divided by.
Yeah, that's what you said multiplied.
Okay. So you subtract here, the slope is delta y divided by delta x. Delta y, the difference in y, is 100.8 minus 16.8. That's the difference in the height between this point and this point. 100.8 minus 16.8. 100.8 minus 16.8. Divided by delta x, the difference between the 2 points, which is 7 feet. So the equation of that line is 100.8K. Tristan has a calculator. How much is this value? 12?
Yes.
And this is 12x. Okay? Let me just make sure this... Okay. That's 12x. Okay? So now, at the distance d, the shear at a distance d from the support, how much is that? You put x equal to 22.5 inches divided by 12 in that equation that we just found. We said the shear at any point is 100.8 minus 12x. At D, V is 100.8 minus 12, and x is 22.5 inches divided by 12 inches per foot.
Will you spell that just a little bit?
Hmm?
Will
So the shear at a distance d from the support, okay, is 78.3 K. How much was the shear at a distance d from the support in example 8.3? Definitely it was a smaller value. 73.8. So it's smaller value, it's smaller than 78.3. Why is that? Because the slope of the line in the previous problem was steeper, right? You started at 100.8 and at the middle you ended by 0. Here you ended by 16.8, so the slope is less. So 78.3. That means that you might need a smaller spacing for the stirrups, right? In the previous problem, you remember the spacing was 5 inches, right, at the beginning. Now you might need a smaller spacing. Let's see now, okay? So this is 78.3 design for that magnitude. So now we need to design. So design stirrups. We need to find the spacing for V ultimate of 78.3 K. You find Vs, which is V ultimate minus phi Vc divided by phi. So that's 78.3 K minus phi Vc, which is 32.018 K, divided by phi, which is 0.75. So Vs is 61.709 K. Okay? So the spacing, the required spacing is AV F yield D divided by Vs. AV is 2. I'm using U-shaped number 3 stirrups. So U-shaped, you have 2 branches multiplied by the area of a number 3 bar, which is 0.11 inches squared, multiplied by F yield, you have 60 KSI, multiplied by D. D is 22.5 inches, divided by Vs, which is 61.709 K. Just always make sure that the units are consistent. This is skips, and then everything else is in inches. So the required S is 4.81 inches. Definitely you have to check the value of S max, okay, which will be larger than this value. We did this in the previous problem. Check S max, okay, as in the previous problem. As in example 8.3. Okay, you're going to have the same values. Okay. So now, how much is the required spacing? So therefore, use S. You cannot have 4.81. You have to round it down. Okay. So I'm going to round it here to the nearest inch. So 4 inches. So the spacing is 4 inches. So here, I'm going to use a spacing. So here the spacing is 4 inches of spacing. Inch. S is 4 inches. That's the first region here. Okay? And then I will decrease that. Sorry, or actually increase the spacing. I will decrease the amount of steel. Okay? I'm gonna have another spacing here and then a third spacing here. In the previous problem, we had spacing of 5 and then 9 and then no stirrups. Here we're gonna use, let's say, 4. That's what you need here. And then we're gonna decrease this twice. Okay? So you can choose any 2 numbers. What I'm suggesting here, okay, is 6 and 9. Okay? So let's use here spacing of 6 inches, and then decrease this again to spacing of 9 inches. Okay? So where is spacing of 6 inches enough? Where, at what point can you provide a spacing of 6 inches?
Find it from the equation.
Find the strength of spacing of 6 inches and find that point where the shear is equal to the strength of 6 inches. Okay? So let's do this. So here for economy, decrease, or actually increase, you're going to decrease the amount of steel, increase the spacing to 6 inches, then to 9 inches. So for 6 inches, V ultimate, the strength of the 6-inch stirrups is VVC plus VVS. VVC was 3218 pounds plus phi, which is 0.75. VS is AV F yield D divided by S, so that's 3218 pound plus 0.75. AV is 2 times 0.11 inch squared. $60,000 psi multiplied by D, which is 22.5 inches, divided by S, the spacing, which is 6 inches. So the strength is, for 6 inches of spacing, the strength is 6,943 pounds. Okay? So at what point the shear is equal to that value? How can you find that point? From the equation. Which equation?
Our line equation we solved earlier.
Okay. So V at the distance x is 100.8 K minus 12x. So I'm just going to put the shear here equal to 69.143 K equals 100.8 K minus 12x. So therefore x is equal to 2.638 feet multiplied by 12, that's 31.66 inches. So when x is 31.66, the shear here, the strength is 69.143 K, and that distance is 31.66 inches. So anywhere beyond this point, 31.66 inches, you can provide spacing of 6 inches. It's going to be enough. Okay? Now, the same. At what point spacing of 9 inches is going to be enough? When the shear, I need to find the strength of 9 inches of spacing and find that point. Okay? So for spacing of 9 inches, how much is the strength? The ultimate is VVC plus VVS. This is VVC is 3218 pound plus 0.75. VS is AV. F yield. D divided by S, which is 9 inches. So spacing of 9 inches will provide strength, a shear strength of 56,768 pounds. So that's the strength of spacing of 9 inches. It's 56. So this point over here, where you can provide spacing of 9 inches, you would have a shear of 56.768 K. Where's that point where the shear is equal 56.768? You still use the same equation. So V ultimate, or V of x, the shear at any distance x, is 100.8 K minus 12x. So put this here, 56.768 K equals 100.8 K minus 12x. So therefore x is equal to 3.67 feet multiplying by 12. That's 44.03 inches. So at a distance x equal 44.03, so here 44.03 inches. At that point, you can provide spacing, stirrup spacing of 9 inches. That's safe, okay? But not before that point. You cannot provide spacing of 9 inches here, but you can provide it here. Okay? So I have 4 inches of spacing, 6 inches of spacing, 9 inches of spacing. This distance is 31.66. This distance is 44.03. So let's do as we did in the previous problem. Find the numbers, the number of stirrups in each portion. Okay? So your beam looks like this. That's the face of the column. This is the center line of the beam. How much is that distance from the beginning to the center? That's 84 inches. I want to provide my stirrups. I'm going to provide my first stirrup at 2 inches from the column, the face of the column. So that's 2 inches here. And then the spacing is 4 inches, right? So one stirrup here, and then this one. So how much is the total distance from the face of the column now? 6, 10, 14, 18, 22, 26, 30, 34. Right? So 34, at 34, that's larger than this 31. But 30, the stirrup before it was at the distance of 30, so that's not enough. So you need to provide that one at 34, okay? To be larger than 31.6. So how many stirrups did we provide now at that spacing? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you can say here you have 8.
There's 9 bars in there.
1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you can say 9 or you can say 8, and the first one you say that it's just a distance of 2. So whatever you want. Okay? Both are correct. So 9, number 3 stirrups at 4 inches. So now how much is this distance from the beginning to that point? That's 34 inches. Okay? And then the next region, you have spacing of 6 inches, right? And that should extend to at least a distance of 44.03 inches. Okay? 44. So the second part here, so I go by a distance 6. So how much is this? 40. And then 44. Okay, so those two here, this is 2, number 3 stirrups at 6 inches. And then the rest is going to be number 9. Sorry, spacing of 9. Okay? So spacing of 9. This is over here, this distance. This is 46 inches. Okay? And then you're going to provide number 9. So 55. Right? 55. And then 64, 73, and then 82, okay? And then the right, or the right half of the beam. Okay? So here, we said this is 82, right? So you can provide those stirrups here, okay? This is number 9, 45, so 91. So here those are 4, okay? This is just right to the middle of the beam. 4, number 3, U-shaped stirrups at 9 inches. Okay? And then so this is the center of the beam over here. That's the center. Okay, and then the other, it's symmetric. The other half is symmetric. Okay? Any question? Okay, on the lecture notes, the slides that are posted on Blackboard, you have an extra example. Please go through it. It's the same, just that the shear force diagram there is a drop in the shear force diagram. The shear force diagram looks like this. You're provided the shear force diagram, okay? So you have a concentrated force at some point. At that point, there is a concentrated force, so that's how the shear force diagram looks like. So just go through that example, okay?
Why did you use 6 and 9 inches? Does it matter? S equals 6 and S equals 9?
No, you just want to go, to increase the spacing. Here you need 4 inches, so you just need to increase it maybe 6, 7, okay? You didn't have to provide 2 different spacings, by the way. So on the test, if there is a problem like this, okay, I will ask you, okay? If I don't ask you to change the spacing, so just design this part, because providing this spacing, 4 inches of spacing everywhere, is a good design, right? It's not a bad design, but it's not economical, okay? So on the test, if I want you to change the spacing when the shear decreases, I will ask you to do this, okay? I have to ask you to do this, and I will tell you what spacing to provide, okay? So that's, because if I leave it up to you, everyone is going to choose a different number, and that's fine. This is what happens in real life. You're going to choose the number yourself, okay? Just 4 inches, okay, I'm going to use 5, 6, 7. It's up to you, okay? Because let's say you provided 4 inches, and then you didn't provide this 6 inches spacing, you just provided the 9 inches right away. That's still a good design, okay? But you're just going to have to provide those for more, distance, for longer distance, the 4 inches spacing. So it's just the choice of the designer himself, okay? Any question? Okay, so that concludes chapter 8, our discussion of the shear force, okay, and design for the shear force. So when you have a shear force, how to resist the shear force? Stirrups, okay? Longitudinal steel bars here, or on the top. What's the purpose of that? the longitudinal bars here,
Oh.
resisting the moment. Okay? The longitudinal bars on the bottom of the beam resist positive moment. Longitudinal bars on the top of the beam usually resist negative moment, or they can be used as compression steel. Okay? So that covers, so far we covered designing for moment, okay, for positive and negative. We covered the design for moment using compression steel, doubly reinforced section. We covered the design for one-way slabs. We covered the design for T-beams, okay? We also covered the design for serviceability, okay, calculating the deflection, how to calculate the deflection reinforced concrete beams, and now we covered the design for shear, okay? Now let's go to the next topic, which is columns, okay? Columns, okay, they have normal force, compression force, okay? So how to design for columns, that's the easiest design so far, okay? So let's go through those slides, okay, that you have on Blackboard. So it's chapter 9. Chapter 9 deals with short columns under axial load, just compression force, okay? Because in frames, you can have a compression force and the bending moment combined, okay? So if you have a compression force and the bending moment, you don't just simply design for the compression force separately and for the bending moment separately, okay? No, you have to combine them together, okay? So now let's just focus on the design if you have a compression force, only a compression force. When you have a column on the compression force, okay, how to design or analyze that column, okay? When we have a compression member, we can categorize that compression element, okay, into 3 different categories, okay? Those are short compression blocks, okay? So this is a very short element, okay, or pedestals, and short reinforced columns, or long or cylinder reinforced columns. What's the difference between the 3? For short reinforced columns here, the very short, the short compression blocks, okay, the ACI code allows you to just design it without any steel. If you don't need to provide any steel reinforcement, you can do that. If the concrete is enough to resist that, so that's fine. But it has to be very, very short, okay? What's the definition of a short compression block? I say it has to be very, very short. So to fall under this category, the height has to be less than 3 times the least lateral dimension. If the height of that element is more than 3 times the least lateral dimension, then it's not categorized as a short compression block, and it has to have steel, reinforcement steel. Even if the concrete is enough to resist the compression force, you have to provide steel reinforcement in that element, okay? It's not a compression block, it's a short column, okay? So if you have a short compression block, you can design it using, just plain concrete, okay? No reinforcement. And the maximum force that can be resisted is the strength of the concrete, okay, that element. So it's the stress FC prime, 0.85 FC prime, that's the stress or the strength of the concrete, okay, multiplied by the area of that element, area gross of that element, okay? And you have to multiply by the factor of safety phi, the strength reduction factor, and phi in that case is 0.65. So that's for the design of short compression blocks, okay? For short compression blocks, you don't need to provide steel, and the strength of it is simply 0.85 FC prime area gross. That's the nominal one. The ultimate strength is just multiplying by phi, and phi in that case is 0.64. Okay? So that's the first category here, the short compression blocks. Okay? If the height of the column is more than this, then it's either a short reinforced column or long or cylinder reinforced column. The difference between both is short reinforced columns are columns where buckling would not happen. Okay? It's short so that buckling doesn't happen. Okay? You compress it, it's just going to fail due to the high compression force, okay? The failure of the material itself, not because of the buckling or instability in the column. While long or cylinder reinforced columns fail not due to the failure of the material, but due to the buckling of the column. Okay? We're not, in concrete, we're not, for reinforced concrete, we're not going to discuss longer cylinder reinforced columns. Not because they don't exist, definitely they exist, okay? You might have a column that is very long, it can, is susceptible to buckling, but it's not a, a popular thing that happens like, I guess, like in this building, all those columns are not cylinder, okay? They are all short columns, okay? So we're going to focus on the, the familiar things, the short reinforced column, okay? So this is what we have here, short reinforced columns. They are, their length is not too large, so they fail due to material failure, okay? And the maximum load supported by those columns is determined according to the dimensions of the column and the material properties, okay? While for the cylinder reinforced columns, you have, instability or buckling, so the column buckles like this, so it depends on the length of the column, okay? The load that can be resisted by that column depends on its length, okay? The more tall the column is, the less load it can resist, okay? We're not going to discuss this, okay? That's actually beyond the scope of our course, okay? For those short columns. So our topic now, we said we have 3 types of compression elements. The first one was so easy, we already discussed it. The cylinder columns, we're not going to discuss it, but we understand that those are long columns. And then we have the short columns, okay? So our chapter is all focused about the short columns. So everything that we're discussing now is about the short columns, okay? Types of those short columns, you can have ties, okay, in those short columns, or spiral columns, or composite columns, okay? Tied columns, ties here, is the same word that we used like for stirrups, okay? It's for transverse steel. So you have your column like this. Let me open this here. Let me open a new that's chapter 9. So in a column, that's a column here. You have a compression force applied on that column, P, a normal force, okay? You have concrete and you have steel. Your steel bars is going to be longitudinal like this, okay, in the direction of the column or the direction of the normal force on that column, okay? And then you're going to have, as we had in the beam, you're going to have stirrups like this, right? But we don't use the word stirrups for columns usually. We use the word ties, okay? But it's the same like the stirrups, okay? It's just that it's transverse steel. So that's transverse. So ties or stirrups are just transverse steel. So what type of transverse steel you're going to have? You can have separate ties, tied columns, just separate ones, or you can have spiral, okay? So in a spiral, it's helical shape, okay? You just have a spiral, just one, and it just goes up, okay? The same steel bar, it's just, helical shape, okay? And so this is the first type here. You have tied columns, longitudinal bars, and then you have ties in between like this. Or you can have spiral columns. Usually spiral columns are provided in round or circular columns, but you can still provide separate ties if you want, okay? And those tied columns are provided in rectangular columns, okay? The third type, if you have a very large load, you can provide a composite column. So a composite column, when your amount of steel that you have to provide is very, very large, okay, you can provide this amount of steel as those longitudinal bars, plus you add in the core of this section here some steel section, a W-shaped, okay, section of steel right in the middle to increase the strength of your column, or steel pipe over here to increase the strength of that column, okay, to provide more steel, more area of steel to the core of the column, okay. So those are the three options that we have here, okay. So comparing the tied columns to the spiral columns, which one is better? Spiral columns are more effective in confining the concrete core, okay? So spirals are much, much better, okay, for columns, okay? But the problem with spirals is what? It's very hard to have in a rectangular column, that's one thing, okay? And even for circular columns where it's relatively easier to have, okay? But still it's more expensive than separate, okay, than ties, okay, separate ties. So spirals are better, but they would cost more, okay? Spiral stirrups are better, but they cost more, okay? So spiral stirrups, the good thing about spiral stirrups is they confine the core of the concrete. So you compress, you have an axial force here, okay, compression force. So the concrete wants to go in that direction, the spiral is preventing it, okay? So the spiral, okay, will give you a confinement to the core of the concrete. So actually it increases the strength, the axial strength of the column, okay? For that reason, if you remember in chapter, I guess, 3, okay? The ACI code says that for spiral stirrups, phi is 0.75. While for separate stirrups, phi is 0.65. You remember this in chapter 3? You remember that equations that we had, right? Phi is 0.65 plus 0.25 multiplied by the strain minus 0.002 divided by 0.005 minus 0.002. That's for separate stirrups, so it's 0.65. Plus that value, or it's 0.75, sorry, this is 0.25, and this is 0.15, and then the same magnitude in the same equation here. So this is for spirals. And this is for ties. Okay? But those are for beams. Those equations are for beams. For columns, you don't have this term. Just 0.75 for spirals and 0.65 for tied columns. Okay? That's all that you have for columns. So phi is either 0.65 if you have a tied column or 0.75 if you have spiral column. Okay? So now we said spirals are very effective in confining the core of the concrete, and we're going to depend on that property, okay, in designing the spirals themselves, okay? When designing the spiral stirrups, we're going to depend on this property, that they are confining the core of the concrete, and that confinement will increase the axial strength of the concrete, or the core of the concrete, okay? So this is what we have here for spiral, okay? This is the spiral stirrups, okay? You have a stress F1, an axial stress on the column F1. When you have an F1, okay, the column wants to expand horizontally because there is something called Poisson's ratio, right? The lateral displacement. So the core of those spirals are providing confinement to the core of the concrete, okay? So this is due to, that will actually give you hoop tensile stress in those spirals, okay? So you compress the column like this, The column won't expand horizontally. The spirals are confining the column, so you're actually putting tension on those spirals. Okay? So the spiral here, there is a tensile force of FSB, the stress in the spiral. Okay? The spiral will fail when this stress becomes what? Yeah, equal to the yield stress, then that's the failure point. The stress in those bars cannot be larger than the yield stress. And now, the stress, the confinement, this confinement now in the stirrup will put stress, okay, horizontal stress on the core of the concrete. We're going to name this F2, okay? So F1 is the axial stress on the column. F2 is the confinement stress on the core of the concrete due to the spiral stirrup. And FSB, okay, F spiral, is the stress in the spiral itself. You understand those three different values? Okay? So now, F2 is horizontal, okay? F1 is longitudinal, FSB is horizontal like this, okay? So the force, if you apply simple mechanics, okay, the force in the spiral over here, which is FSB, 2FSB multiplied by the area of the spiral, have to be equal to the force, the confinement force, which is F2 multiplied by the area over which this is applied. So actually, to understand this, we're just going to study a plug, part of the column, of a height of that S. S is the pitch of that spiral. So what's that? S is the distance over which, that spiral stirrups make a complete round. Okay? So that's the pitch over here. You have S. So we're just studying a part with that height S. Okay? And equate the forces here. So you have 2 FSB multiplied by the area of the stirrups equal F2 multiplied by S and D core. Because that's what we have in one loop. Okay? In that loop, in that height S, how much is the area provided by the stirrups? You remember we used rho, right, to provide or to define how much steel you have in comparison to the area of the concrete, right? It's rho was area steel BD, so it's an area of steel divided by the area of the concrete, right? That's rho. Usually to define how much stirrups, the area of the stirrups that you provide, we use again rho, okay? But rho here is not a ratio between the areas. It's a ratio between the volumes. The volume of steel that you provide at a distance S divided by the volume of concrete in that distance S. Okay? So we have a volumetric rho here. So I'm just going to skip those and then I'm going to come here. Rho for the stirrups, okay? It's the volume of spiral in one loop, so it's volumetric ratio, not area ratio, okay? The volume of spiral in one loop divided by the volume of concrete core for a pitch of S, okay? So it's V of the spiral divided by the V of the core. How much is the volume of stirrups in one loop? The area times the length, right? So the area, that's the area of the spiral here, times the length in one loop, which is equal to the perimeter, right? So the perimeter is pi d. So pi d here, we use d of the core, the inside diameter of the core of the concrete, the inside diameter of the beyond the stirrups, minus d of the spiral. Sorry, this is dc is to the center of the stirrups, okay? Minus d spiral, okay? So divided by the v core, the volume of the core, which is S, the spacing multiplied by the area of the core. So S multiplied by the area, which is pi d squared divided by 4. Okay? That's the volume of the steel divided by the volume of the concrete in just the distance of S. Is that clear? So having this here, just move the 4 up, so 4 ASP dc minus d spiral divided by S. S is the spacing or the pitch divided by dc squared. Assuming here this is almost equal if you just neglect this part. So DC and DC, if you assume that this is 0, so DC and then DC squared over here, so you end up by 4 area spiral divided by SDC. So that's rho of the spiral. It's 4 ASP, that 4 multiplied by the area of the spiral, okay, divided by S, the spacing or the pitch, divided by DC. Any question? So we're going to continue from here next time. Your homeworks are here.
We don't have class this Monday? Or next
Next
Monday?
Monday.
That's what
Yeah,
I
they'll
mean,
be
obviously
out
that's
of
what I mean.
town.
Yeah.
And then we'll have our test Wednesday.
Gotcha.
Right? No class on Monday, test on Wednesday?
What, next week?
Yeah.
Yeah, next week, yeah.
Yeah. I didn't mean today. You're here today. No, next week. And then we'll have class again on Friday. You'll be back.
Yes.
Okay.